Hi, this is part two of my rational functions mini lecture, and what I'm going to show in this part two is a particular example. It's probably one of the most simplest functions you'll ever encounter in rational functions, and both of them are polynomials. 2x minus 4 on top is a polynomial, degree 1 is linear, and x plus 1 is also linear, so definitely a rational function. And I put down that I have a coat with holes just to remind myself of all the things I have to do. And of course, the I stands for the intercepts, and the first thing we'll need to do is find the x-intercepts. Now, how do you find the x-intercepts is when you set the function equal to 0. In this case, the function is going to equal 0 only when the numerator is equal to 0. So 2x minus 4 is equals to 0 only when x equals 2. So at x equals 2, that is the place where it's going to cross the x-axis. So you mark over here 1, 2 units, and there is a doorway there. Basically, the graph will go through that point. Now, something we learned back in 5.1, polynomials, if the degree is odd, and 2x minus 4 is definitely odd degree because it's 2x in the first, we learned that they will cross into the other side. They don't just touch and go up the opposite direction. So the same thing takes place here. So I'll put a little C here to remind myself when I start tracing this graph that the graph will actually cross. So if it's right here where my finger is, it's going to go up through this side. It won't just come up and touch it and come back. So the C stands for crossing. So that's the x-intercepts. Now the y-intercept, and there's only one because it's a function, is we set x equal to 0. And if you set x equal to 0, you get 2 times 0 minus 4, 0 plus 1, so 0. So that'd be negative 4, I think, when you finish it. So 1, 2, 3, 4 down here. Okay, so of course it crosses there because it's got to go from one side to the other side. And if it bounced, then you wouldn't even have a function to begin with. So x-intercept, it's a 2. The y-intercept is a negative 4. Okay, so that's the intercept. So the I is done. Now what we got to do is have a coat with holes. Now the HA is the horizontal asymptote. Now remember what I said in part 1, that if the degrees are the same, you're going to have a horizontal asymptote. So this one does have the degrees that are the same. 2x to the first minus 4 over 1x plus 1. So the degrees on both these are 1 on top and the bottom. Now one thing I didn't tell you how to do it is how you really figure this out. Well, when the degrees are the same, the horizontal asymptote is the quotient of the leading coefficients. So the leading coefficients are 2 and 1. That's the leading coefficients. So the horizontal asymptote is just the quotient of those two numbers, 2 divided by 1, which is 2. A lot of people think it's the quotient of the exponents, and that's not true. It's the quotient of the leading coefficients. So if this one was a 3 and this one was a 2, then the horizontal asymptote would be y equals 3/2. So, but in this case, it's 2 over 1. So there is a horizontal asymptote at 2. Now understand what the horizontal asymptote really means. All this means is the graph is actually going to get very close on each extreme. That's what's called the end behavior. And so the graph won't, when it gets out to negative infinity, it's not way up here and it's not way down here. It's hovering around this dotted line. And it's hovering around the dotted line on this end too. So that's the whole point of the horizontal asymptote. Now in between the infinities, so to speak, it could be somewhere in here. And as a matter of fact, it could cross the horizontal asymptote. But on the extremes of the asymptotes, it's just merging into it. It's getting really, really, really close. So in this case, the horizontal asymptote is, like I said, y equals 2. Now the vertical asymptote, now this thing has already been simplified. 2x minus 4 over x plus 1. There's nothing to reduce. And so there's no common factors. And by the way, since there's no common factors, there's no holes. So we won't have any of these to worry about to begin with. And I will do in part 3 my one that has holes in them. So, but on this one, there is a vertical asymptote. And the vertical asymptote is setting the denominator equal to 0. And so x equals negative 1. So that's the vertical asymptote. So there's a vertical dotted line right through there. So now, does it cross the horizontal asymptote? Well, let me give you a little bit of experience advice. It's just based on experience. Whenever you have a linear over linear, it never crosses the horizontal asymptote. But that's you can only make that statement if it's linear over linear. What would you do to figure it out, though, is you set the function 2x minus 4 over x plus 1, set that equal to the horizontal asymptote, which happens to be y equals 2. So we set that equal to 2. And when you try to solve that, now if you get a value of x, say let's say it's x equals 3, then you'd have to come over here at 3, 1, 2, 3, and put a dot right there in the horizontal asymptote. But it won't be 3, it won't be anything, because when I try to solve this, it'll give me something that can't be true. So you get 2x minus 4 equal 2 times x plus 1, and you get 2x minus 4 equal to 2x plus 2. And then the 2x's cancel out, leaving you with negative 4 equals negative 2, positive 2. And there's no way that can be true. And so, like I said, whenever you get a linear over linear, you can kind of skip this part right here. So this basically says the horizontal asymptote is off limits. The vertical asymptote is always off limits. So basically, the graph always just kind of merges into these things. And so that's the C on the coat. Now, the oblique asymptote, remember while ago in part 1 I said that the oblique asymptote, you're only going to have those if the degree on top is bigger than the degree on the bottom. So in essence, these are kind of like mutually exclusive. If you have one, you don't have the other. Horizontal asymptote, if you have this one, you will not have an oblique asymptote. And the good news is most of those will be in this case. So, but for those ones who will not have a horizontal asymptote, will definitely have an oblique asymptote. So it's going to have one or the other. Okay, and the good news is most of them will have horizontal asymptotes. And in another part of my mini lecture, when we do an oblique one, I will show you how to do that one later on. Okay, and like I said, there's no holes in this graph. So this is pretty much it. I went through the whole process, and I'm ready to trace the graph, believe it or not. So I have these 2 points, and these 2 points are kind of like doorways, if you will. That's the analogy I like to use anyway. The graph actually will go from one doorway to the other doorway, and it will cross the threshold to the other side. Okay, now it's like the graph is actually trying to get very, very close to an asymptote, and that's the y equals 2. So when it comes back this way, it gets close to the asymptote this way. Now, here's the deal. When you go on the right side of -1, actually on the right side, when we go on the left side of -1, it's either going to be up here, down here, or up here. Because you got to remember, it doesn't cross the horizontal asymptote. So the graph itself is kind of like compartmentalized. It's either completely down here, up here, or completely down here, one or the other, but not both. Now, if it's down here, it's got to get close to this asymptote and get close to this asymptote. Okay, but in the process, it has to cross the x-axis, because if it's right here, and then since you can't cross this asymptote here, we've already said that you can't do the C, then it can't go back up. So it has to go down, but if it goes down, there's got to be an x-intercept somewhere on the left side of -1, which there isn't one. So by a process of elimination, since there's no x-intercept here, it has no choice but being up here. But let me give you something else to chew on here. If the graph ends negatively, 95% of the time, if it ends negatively on one side of the vertical asymptote, it starts positive on the other side. There is an exception to that. If the degree on the bottom is even, if you have an even root on that vertical asymptote, then it would bounce. It would actually be on the same side. Most of the time, most of your problems that you're going to have, you've had very few problems that will actually do that. Most of your ones that it's going to end positive, it will start negative on the other side. Or conversely, if it ended negative on this side, it would start positive on the other side. And this is the complete graph of this function. Now, you're like, how accurate is that? No, I don't know. I mean, you could get a little bit more accurate by plotting more points to get more key points on this. And I think that's very time consuming. All we really want to do is to get a rough sketch of the graph. That's all we really want. We want to know whether vertical asymptotes, whether horizontal asymptotes, and kind of put the graph in the appropriate compartment, if you will. And but this is, like I said, this is one of the easier examples. It's a linear over linear is one of the easier type problems. You're only going to have one vertical asymptote. You're going to have a horizontal asymptote. It doesn't cross the horizontal asymptote. You can't get much more simpler than that. They get a lot more trickier than this one. So, but this is part 2, end of part 2. That's it.